Surfing Math Lessons presents what you should know before calculus. Before we start, let us first answer a question: what is calculus? Informally speaking, calculus is a mathematical theory which explores the concept of limits and its consequences. Limits are mainly used to better understand real value functions of a real variable. Let us start by taking a global approach and look at how calculus is structured. As mentioned before, the theory of limits is mainly used to better understand real values functions of a real variable. This theory has important implications. The first is a theory of differentiation. This theory explores how a function's behavior changes with changes in its argument. The second implication is the theory of integration. This theory enables techniques that help us calculate how much area is bounded between the graph of a function and the x-axis. Although differentiation and integration may seem like completely different theories, the two are connected. The theories of limits, differentiation, and integration are the three main pillars on which calculus is built on, a sort of triforce, if you will. Since differentiation and integration are consequences of the idea of limits, it's only natural to start a calculus study with the concept of limits. However, to build a strong mathematical foundation, we will need some prior mathematical knowledge. We start with a short review on some aspects of functions and naturally move onward from them. Consider two general or unspecified non-empty sets called A and B, represented by the green and red rectangles on the left and the right respectively. These sets have elements in them which we bring forward and represent them as white dots inside A and B respectively. A collection of arrows emanating from some of the points in A and pointing to points of B defines a relationship, one which I will denote by the small letter R. The starting and ending points of the arrows defines two subsets called the domain and image of the relation. A function is a relation which satisfies the additional requirement of having no domain points with more than one arrow. For example, if we consider the following collection of arrows, note that there are two of them emanating from the same domain point. Thus, this relation is not a function. This key feature is part of the definition of a function and is usually expressed via what is known as the vertical line test. Hence, in order to obtain an example of a function, we can take this previous example and slightly modify it as to satisfy the vertical line test. Namely, choose one of the arrows in orange and drop the other one. The resulting relation is a function. We will usually use the letter F to denote relationships which are functions. So far, this type of illustration of a function is very convenient for visual purposes. However, for real value functions of a single real variable, a more suitable representation is the following. The sets A and B are each replaced by a copy of the real number line. A relation or function is then given by a collection of arrows, each of which emanates from a domain point and points to its image. This representation can be drastically improved once we consider the Cartesian product. In our case, this is easy. We take both copies of the number line used before and intersecting perpendicularly at 0, thus obtaining the x and y axis of a plane. Our arrows in the previous representation now become graph points in the plane. This representation has the advantage of compactifying the important information, namely, by attaching scales or numerical margins to both the x and y axis, the information contained in the domain and range sets of a function can now be easily accessed throughout the graph points in the grid. For example, consider the point P is equal to 2, 4. This point's domain and range can be easily found by checking where the grid lines intersecting P intersect the x and y axis, respectively. Many functions have domain and range sets which contain an infinite number of points. Some of these functions may be represented throughout the following illustration. Since it's not possible to sketch an infinite number of arrows from domain points to their images, it is not possible using this representation to determine what the function f actually is. This is where using the more compact representation of the graph of the function becomes invaluable. In this case, I have sketched the graph of the function y is equal to 1/2 x squared. A function's behavior is heavily influenced by the nature of its domain. This is more easily seen by considering the previous examples in the special case of the function y is equal to 1/2 x squared. Take a look at the following side-by-side comparison. Clearly, the graph of the functions is vastly different from each other, even though the underlying function in both of them is the same. The one on the left is drawn by sketching 4 isolated points in the plane, while the one on the right can be drawn with a single stroke motion. This suggests that intervals are very special sets of real numbers when they arise as the domain sets of functions. Thus, in order to better understand real value functions of a single real variable, it is crucial we ultimately better understand the numerical model of the real numbers. I will now proceed to go over the numerical model of the real numbers and some of its more important properties. During this journey, we will see how the idea of limits naturally emerges from exploring the real number line. For this, I will make use of a set of notes I have written. In this second part of the video, we are going to be taking a look at the numerical model of the real numbers in some detail. We do this by making use of examples, observations, and common sense as motivators for the veracity of results. The numerical model of the real numbers can be represented as all points lying in a straight line stretching without end in opposite directions. Just as before, this model is denoted by the double stroke capital letter R. The numerical model of the real numbers is born out of necessity to solve ever more complicated problems. It can be obtained from the natural numbers throughout a series of numerical model extensions. By a numerical model extension, we mean incorporating additional numbers into an already pre-existent model in such a way as to obtain a newer model which retains some key features from the old one and also provides us with solutions to previously unsolved problems. Observe that in this particular extension, from the natural numbers to the real numbers, the integers and the rational numbers appear. With the construction of each newer model, certain unsolvable problems now have a solution. For example, if one considers the numerical model of the natural numbers and the equation x plus 2 is equal to 1, then this equation has no solution in the naturals. However, after extending into the integers and trying to solve the equation in the newer model, this equation has a solution, namely x is equal to minus 1. That is to say, an equation which involves only natural numbers has a solution which is not a natural number but an integer. Likewise, the equation 2x plus 1 is equal to 0 is an equation involving only integers, but the solution is not an integer. One has to extend the numerical model of the integers into the fractions in order to find a solution, namely x is equal to minus 1/2. And finally, the equation x squared minus 2 is equal to 0 is an equation involving only rational numbers, but the solution is not a fraction. One has to extend from the rational numbers into the reals for this equation to have a solution, namely x is equal to plus or minus square root of 2. The details of each particular extension process depend on the numerical model one is dealing with and also of the problem one wants to solve. These specifics are not particularly useful to us and also can be quite technical. For that reason, we do not speak more on the subject, but rather emphasize on what is important. Namely, that the real numbers is a well-built numerical model constructed in order to find solutions to many previously unsolved problems, and since it's obtained throughout the chain of numerical model extensions above, we have the following inclusion of sets. That is, that the natural numbers is contained in the integers is contained in the fractions, and the fractions is contained in the reals. So far we have taken a look at the origins of the real numbers and why are they useful. In order to expand this discussion, I am going to be introducing 5 key properties of the reals. The first property tells us that any real number has a numerical expansion associated to a choice of natural number called the base. The two more widely used expansions are the decimal expansion and the binary expansion, which correspond to bases 10 and 2 respectively. In the case of the decimal expansion, this means that for any real number a, there is an integer p and a sequence of digits di, which allows us to write a in the following form. That is to say that a can be represented by making use of its integer part and fractional part. For example, the numbers 34/16, pi, and square root of 150 have the following decimal expansions. Since most aspects of the real numbers depend on their intrinsic nature and not in the way in which we represent them, we use the decimal expansion exclusively moving forward. The second property tells us that they are real numbers which are not rational. These are called irrational numbers and they exhibit the feature that their decimal expansion is never ending nor repeating. For rational numbers, this is not the case. Either their decimal expansion ends after some decimal place or repeats indefinitely. The following example contains 3 real numbers, 2 of which are rational and 1 which is irrational. Note that for the 2 that are rational, either their decimal expansion ends or repeats, and in the case of the one which is irrational, its decimal expansion never ends nor repeats. The third property tells us that the set of real numbers is ordered via the inequality less or equal to. This means that given any 2 distinct real numbers, we can always tell which of the 2 is bigger and which of the 2 is smaller. This comparison translates to a relative placement of the 2 numbers in the real number line. The fourth property tells us that between any 2 distinct real numbers, we can always find another one. It is this property that guarantees that the real number system has no gaps in it and that the standard representation of the reals has a straight line is valid. And finally, the last property tells us that given any 2 real numbers, we can always determine exactly how far apart they are from each other. In the real number line, numbers are represented as points, and this property corresponds to the distance between those points. Now that we have these 5 properties, we are ready to tackle problems involving computations with real numbers. From a computational standpoint, the second property has its drawbacks. One may not be able to always do exact computations. For example, consider the following question. How do you carry out the addition algorithm for calculating the exact value of the real number square root of 2 plus pi? If we write square root of 2 and pi using their respective decimal expansions, then the addition algorithm asks us to start by adding their last decimal place first. However, in this case, both numbers have non-ending decimal expansions. Hence, the addition algorithm cannot be carried out. A viable workaround to this problem is to trim or truncate the decimal expansion of those numbers in the computation that have non-ending decimal expansions and then perform the computation. The end result is not the exact solution, but rather an estimate of it. For example, we can estimate the value of square root of 2 plus pi by first truncating each number's decimal expansion to say their second decimal place, and then carrying out the addition algorithm. This brings the question of choice. Why did we truncate each number in the computation to their second decimal place and not some other decimal place? That is to say, does this choice matter? The short answer is that the choice of truncating to a certain decimal place has an impact in the accuracy or precision of the estimate with respect to the exact solution of the computation. In general, the accuracy of the estimate and the amount of work in a computation both increase as more decimal places are used. The quantity that tells us how far apart is our estimate from the exact value is called the error and is denoted by the capital letter E. By the fifth property, the error can be interpreted to be the distance between the estimate and the exact value in the real number line. I want to mention that the concept of rounding up or down a number runs in parallel with that of truncating a real number's decimal expansion. In this parallel discussion, the rounding error can be found by using the formula for the error E. Now suppose we are asked to find the error of using the number 1.414 as an estimate for square root of 2. Then we see that this difference also has a never-ending expansion, and hence the error cannot be calculated exactly. In general, this is the case as the error is a real number by definition. The solution to this difficulty is to change our approach, namely, instead of asking for an exact numerical value of the error, we ask for an estimate of it which is sufficiently small. This is where the ordering of the real numbers naturally appears. With all these things in mind, consider the following example. To estimate square root 2 plus pi with an error smaller than 0.01. Notice how the phrasing of the example is more in tone with the numerical model of the reals. That is to say, instead of asking for exactness, we now ask for an estimate with a certain precision from the exact value of the computation. To solve this example, we first look at the upper bound for the error and notice that it uses 2 decimal places. We then add square root of 2 plus pi. By using enough decimal places has to have more decimal places than the bound. Observe that by truncating our estimate so that it has 2 decimal places gives us another estimate with the desired precision. Indeed, the error of using 4.55 to estimate square root of 2 plus pi is around 0.006. From this example, we can extrapolate 2 things. First, the more decimal places we use, the closer our answer is to the exact value, and thus the smaller the error. The second is that too few decimal places can yield a bigger than desired error. For example, truncating the answer above to the first decimal place yields an error of around 0.05, which is 5 times bigger than requested. Before we move on with the discussion, let us recap some of the important points above. The first is that exact calculations involving real numbers are in practice quite rare. This is due to the nature of most real numbers to have a non-terminating decimal expansion. The second is that estimates have a natural error associated to the number of decimal places used in a computation. This error can be guaranteed to be small provided enough decimal places are used. The third is that enforcing the error to be small is equivalent to requiring the error be smaller than some fixed number. If delta is greater than 0 represents a small real number of our choosing, we can guarantee the error is smaller than delta by making use of one of the inequalities below. This number delta can be interpreted as the smallest error that cannot be allowed. Any error smaller than delta is acceptable, and any error bigger than delta should not happen. And finally, the error inequality lies at the center of calculus and may be interpreted in a different number of ways. By properties of absolute value, it can be rewritten in the following two forms. So far, we have seen the real numbers from a purely computational perspective. We now take a different point of view and explore the real numbers by making use of the real number line. To start, consider the copy of the numerical model of the integers contained inside the real numbers. Integers are distributed uniformly in the reals. That is, any consecutive pair of integers lie at distance 1 from each other in the real number system. Hence, we can take our standard representation of the real numbers as a straight line and refine it by tagging all integers in it. This in turn induces a partition of the real line as a collection of disjoint intervals of the form a plus 1, where a is an integer. Each interval of the form a plus 1 contains all real numbers whose decimal expansion has integer part a. This allows us to start tracking a real number's location in the real line relative to the integers, or better yet, relative to the number 0. For example, the element 53.3 lies somewhere inside the interval 53-54. Let us consider another example to find the location of the element 3.71 in the real line. Notice that this number's integer part is 3 and thus lies somewhere inside the interval 3-4. This gives us an estimated location. However, we can improve it by making use of the number's decimal places. To do so, let us concentrate our attention to the interval 3-4 depicted now by the color orange. I call this process zooming inside the interval. In the same way the real line was partitioned into a collection of disjoint intervals, we can do a similar process to the interval 3-4. Since the number we're tracking is represented using decimal expansion, we can partition the interval 3-4 into 10 equally spaced intervals of distance 0.1. Then the first decimal place in 3.71 tells us in which of these subintervals the element is. To be more specific, each of these subintervals is tagged with a digit between 0 and 9. We then associate the number's first decimal place with the corresponding tag subinterval. In the case of 3.71, its first decimal place has the digit 7, and thus the element 3.71's location can be tracked to the subinterval tagged with the digit 7. We can still further improve our tracking by now considering the interval in blue, that is, the interval 3.7-3.8. We do this zooming process one more time, namely, take the interval 3.7-3.8, subdivided into 10 equally spaced subintervals, each of distance 0.01, and tag each of them using a digit between 0 and 9. Then, find the element's location using the second decimal place's digit. Thus, 3.71 lies as the left endpoint in the interval 3.71-3.72. With this, we have seen a real number's decimal expansion does not only represent a numerical value that allows us to do computations, but also represents the number's location in the real line relative to the copy of the integers. Before moving forward to the next topic, let us briefly review the important ideas over the last couple of pages. First, a real number's numerical expansion can be used to locate it in the real line relative to the copy of the integers lying inside the reals. Second, the process of finding an element in the real line with respect to its decimal expansion involves identifying the interval a plus 1, where a is the number's integer part, followed up by a subdivision of this interval into 10 equally spaced subintervals. Each of these subintervals is then marked with a digit between 0 and 9. We then track our element to the subinterval those marked corresponds to the digit in its first decimal place. This process is then slightly modified and applied in a nested way over a number of times, depending on how many decimal places are provided in the element's decimal expansion. We saw this in the example of finding the location of the element 3.71 in the real line. Third, for those real numbers whose decimal expansion never ends, the subdivision and summing processes also never end. Thus, we are able to track an element's location in the real line up to the precision we can track an estimate of it. However, keep in mind that such elements have an exact location in the real line. We are just not able to find it by using a finite process as above. And lastly, we may think about a number's decimal expansion as being derived from the process above. That is, if we start with the real line, we may assign to any point in it a numerical representation based on its location. This is done relative to the copy of the integers and collection of subintervals obtained from the subdivision process. With these two different points of view at our disposal, we are ready to start a discussion on the ideas behind the concept of limits. Recall that the error of estimating a real number c is calculated via the equation E is equal to the absolute value of x minus c, where x is the estimate and E is the error. Also, recall that in general, the error cannot be calculated exactly, and thus we need a way to control it. This constraint is enforced by making use of the inequality E is smaller than delta, where delta is a small positive number of our choice. Moreover, recall that the inequality E is smaller than delta is equivalent to the inequality C is smaller than delta, which is smaller than X, which is smaller than C plus delta. This double-sided inequality may be interpreted in the following way. For a choice of delta, all good estimates of C with respect to the delta value lie strictly between C minus delta and C plus delta. That is to say, for a choice of delta, all good estimates of C with respect to delta are points inside the open interval C minus delta, C plus delta. This interpretation motivates the following definition. The delta neighborhood of a point C is defined to be the open interval C minus delta, C plus delta. Observe that if x is an estimate of c, then x may or may not be a point in the delta neighborhood of c. However, if x is a good estimate of c with respect to the delta value, then it must be in the delta neighborhood of c. That is to say, the delta neighborhood of c contains all good estimates of c with respect to the chosen delta value. If we consider the delta neighborhood of c for different choices of delta values, then we see that delta neighborhoods satisfy the following property. Delta neighborhoods of c are nested intervals. That is, if delta 1 is strictly smaller than delta, then the delta 1 neighborhood of c is contained in the delta neighborhood of c. This is more easily seen from the viewpoint of the real line. From this, it is implicit that every good estimate of c with respect to delta 1 is also a good estimate of c with respect to delta. This nested property of delta neighborhoods of c motivates the following idea. By requiring our estimates to lie in an ever-increasing sequence of smaller and smaller delta neighborhoods of c, our estimates get closer and closer to the exact value of c. This is the basis for the idea of approximations in the real line. The goal now is to generalize this notion of approximations to subsets of the real line. Definition: let S be a subset of real numbers and let C be a fixed real number. If, for every delta greater than 0, the set S has a point inside the delta neighborhood of C, which is different from C, then we say that S is a set that approaches or approximates the element C. A generic figure that may help visualize this definition is the following. Here the point C is fixed, and the margins in yellow correspond to the position of elements of the set S in the real line. As you can see, the elements of S cluster around C, leaving no small interval around C without some element of S in it. Encoded in this definition is the following information. If the set S approaches C, then S has a good estimate of C for any choice of delta value. That is to say, S contains a good estimate of C up to any desired precision. This definition of an approximating set relies on both the set S and the point is approaching. It only makes sense to give this point a special name. Definition: let S be a subset of real numbers and let C be a fixed real number. If the set S approaches the point C, then we will say that C is a limit point of the set S. Let us now briefly reinforce these concepts by making use of a concrete example. Example: consider the set of all real numbers of the form 1 over n, where n is a natural number and the fixed real number C is equal to 0. We want to show that S is an approximating set of 0. or equivalently that 0 is a limit point of the set S. To do so, all we need to do is verify that the set S contains, at the very least, one good estimate of C with respect to any possible value of delta. An easy verification yields that the good estimates of 0 with respect to a choice of delta are those numbers strictly between minus delta and delta. Let us first verify that the set S contains at least one estimate of 0 with respect to some predetermined values of delta. First, if delta is equal to 10, observe that the number 1 is in the set S and a good estimate of 0 with respect to this particular value of delta. Second, if delta is equal to 1, notice that the number 1/2 is in the set S and a good estimate of 0 with respect to delta is equal to 1. And lastly, if delta is equal to 0.0007, observe that the number 1 over 10,000 is in the set S and a good estimate of 0 with respect to this particular value of delta. At this point, we have verified that the set S contains a good estimate of 0 for 3 specific values of delta. However, this does not demonstrate that the set S approaches 0. This is due to the requirement of a good estimate of 0 with respect to every possible value of delta, as per the definition. In fact, this requirement is so strong that we cannot fulfill it by checking it case by case, as there are an infinite number of possibilities for the delta value. This is where some abstraction is needed to deal with all cases simultaneously. To finish up the example, I will pull a result from real analysis which illustrates a key property of the set S. This result may be seen to be correct by examining the graph of the function f of x is equal to 1 over x. Theorem: the Archimedean property of the real numbers. We can always make the number 1 over n as small as we wish by making n be a sufficiently large natural number. With this result at our disposal, we can complete the example as follows. Let delta be any positive real number. By the Archimedean property, there exists a natural number n such that 1 over n is strictly smaller than delta. But then the element 1 over n is in the set S by definition, and thus the set S contains a good estimate of 0 for every possible delta value. That is to say, the set S approaches or approximates the number 0. We could have worked this example slightly differently by observing that the number n is equal to the ceiling of 2 over delta is a natural number, and that 1 over n is smaller than delta over 2, which is smaller than delta in this case. Here, the dependence of n on the delta value is explicitly stated. Let us now explore some facts about approximating sets. First, a limit point has many approximating sets. For example, the sets S1, S2, S3, and so on all approach the point C. Second, an approximating set must be infinite. That is, the approximating set must contain an infinite number of points in it. This is a consequence of the definition of approximating sets requiring a good estimate for every possible delta value. And lastly, intervals are special types of approximating sets. They approach every point in them and also their defining endpoints. Before moving on to the last topic on this set of notes, let us briefly outline the main ideas in this subsection. First, the concept of estimating a real number C and its associated error were reinterpreted to construct the notion of delta neighborhoods. These neighborhoods are then used to specify good estimates of C and naturally lead to the notion of approximations. Second, an approximating set may approach many limit points, and a limit point may have many approximating sets associated to it. Hence, we must always specify the approximating set and the limit point in order to make sense of either of them. Third, given an approximating set S and a limit point C, the set S contains an infinite number of points clustering around C. And lastly, intervals are very special. As approximating sets, they approach every point in them and their respective endpoints. I also leave you a comment in the form of an important box regarding the terminology used in this subsection. We now further refine the concept of approximations by using the concept of directions on the real line. The goal of this last section is to define the notion of an approximating set approaching any of its limit points via a single direction. I will first introduce an elementary way to define directions on the real line and then use it to achieve our goal. Recall that the set of real numbers is ordered via the inequality less or equal to. This ordering allows us to do many things. For example, comparing elements or enforcing a small error in a computation, or even encoding an infinite amount of data. This later observation is more clear when we think about intervals, say the open interval AB, which contains uncountably many elements. In this notation, the open interval AB uses the symbols A and B, which are not in the interval itself, but are limit points of it. Let us now define the notion of directions on the real line. The ordering less or equal to of the reals defines two directions in the following way. Let C be any real number. Then, the first direction is defined to be from the right of C, and is obtained by considering elements which are bigger than C in the ordering. The second direction is defined to be from the left of C, and this direction is obtained as the opposite of the first direction. That is, this direction is obtained by considering elements which are smaller than C in the ordering. To get a better perspective on this, let us use a visual aid. Here the point C divides the real line into two disjoint intervals called the left of C and the right of C respectively. Directions are then obtained by moving along the respective intervals towards the point C. In the same way C divides the real line into two disjoint intervals, it also divides every single delta neighborhood of it into two one-sided delta neighborhoods. Let us now restate the definition by using one-sided delta neighborhoods and then move to define approximations via a single direction. Recall that a set S approaches a point C if every delta neighborhood of C contains an element of S different from C. Observe that since the point C must be excluded, the definition is equivalent to requiring that the set S intersects at least a one-sided delta neighborhood of C for each delta value. Even with this restatement, the definition doesn't give us control on the direction of approximation, like in the following picture. Hence, to achieve our goal, we refine the definition of approximating sets as follows. Definition: let S be a set and C a fixed point. We're going to say that S approaches C from the left of C if every left one-sided delta neighborhood of C contains an element of S. That is to say, the set S must intersect every left one-sided delta neighborhood of C. We also have a similar definition for when the set S approaches the point C from the right of C. Note that expressing this definition formally is very short. Let us work on two examples. Example: let I be the open interval AB. We know both A and B are limit points of I. To better understand how this interval approaches A and B, we need to know how all one-sided delta neighborhoods of A and B respectively intersect the interval I. Let's do the case of the left endpoint A. For any delta 1 greater than 0, the intersections of the one-sided delta 1 neighborhoods of A with the interval I are as follows. This then shows that the interval I approaches its endpoint A from the right of A exclusively. A similar analysis can be done to the endpoint B to conclude that the interval I approaches the endpoint B from the left of B exclusively. To bring this into a more appealing form, consider the following visual aid. Here the interval I is represented by the color yellow, and selected delta neighborhoods of A and B respectively are specified. Within these neighborhoods, we then highlight using red and blue colors the one-sided delta neighborhoods respectively. Now the non-empty intersections are easier to spot. Second example. Consider the point C is equal to A plus B over 2, where A and B define the same open interval as in the previous example. Then, by definition, C is the midpoint of the interval I, and thus for every delta greater than 0, we have the following intersections. That is, the interval I approaches the point C from both the left and the right of C. From these two examples, it's evident that there are only three possibilities for a set to approach one of its limit points. These possibilities are stated in the following observation. A set S may approach one of its limit points C either from the left of C, or from the right of C, or from both the left and the right of C. Now that the notions of approximations have been refined to include single directions, we would like to formalize them using symbolic notation in order to be more efficient and write less. This is done in preparation for when we have to do limit computations in calculus. So, our new objective is to encode the above notions into a notation that is convenient and practical for carrying out computations, which will make reference of the approximating set, the limit point, and the direction of approximation. For this, we take inspiration from the number 0. That is, observe that any open interval containing 0 approaches 0 from the right of 0 through all positive numbers and approaches 0 from the left of 0 throughout negative numbers. Hence, for the limit point 0, a sign of plus or minus can be associated to the direction of approximation. We use this to construct the following notation. Here, S is the approximating set and C is the limit point. An arrow is then used to denote that the approximating set S approaches the limit point C. A superscript on the limit point of plus or minus is then used to indicate the direction of approximation. A plus sign denotes from the right of the limit point. A minus sign denotes from the left of the limit point. And if no superscript of plus or minus is indicated, then it means that the set S approaches the limit point C from both the left and the right. Let us now review a previous example and apply this notation. Example. Recall that the set S of all fractions of the form 1 over n, where n is a natural number, is an approximating set with limit point 0. As we saw before, the clustering of S around 0 happens from the right of 0. We can then express all of this information by simply writing the symbols S, arrow 0, superscript plus. That is to say, S approaches 0 from the right. We now do a small modification to the above notation, making it more in tone with calculus. The change is simple. Start by defining a variable over the approximating set. Then replace in each of the previous notations the approximating set's symbol with that of the variable. To read the new notations, simply use their previous versions and replace the name of the approximating set by that of the variable. If you are interested, I leave you a small discussion box detailing the main reasons for this change. The idea of limits can now be motivated by the following two questions. First, how does a function behave during the clustering of its domain set around one of its limit points? And secondly, can this first question be somehow understood by considering whether the range set of the function clusters around one of its limit points? We now proceed to end up this video with a summary of the main ideas in this last subsection. First, the real numbers come equipped with an ordering given by the inequality less or equal to. We use this inequality to define the notion of directions on the real line. There are only two directions which we define to be from the right or from the left of a reference point. Second, we combine the concepts of approximating sets and that of directions to define the notion of an approximating set clustering around a limit point via a single direction. Naturally, this notion is made precise throughout the use of one-sided delta neighborhoods of the limit point. Third, intervals are very special types of approximating sets. Not only do they approach every point inside them, but also approach their respective endpoints. Fourth and fifth, we constructed a convenient and effective notation that encodes the approximating set, the limit point in question, and the direction of approximation. This notation was then modified for calculus by replacing the approximating set by a variable defined on it. And lastly, the main objects of interest in calculus are real value functions of a real variable. The study of these objects naturally involves the understanding of their domain and range sets and their respective limit points. Hence, of particular interest is a function's behavior as their domain set clusters around a limit point. With the notions and ideas presented in this review, we have fortified our mathematical foundation in preparation for calculus. In an upcoming video, we start a calculus journey by intuitively introducing the concept of limits. A list of 10 practice problems is available after the following animation. Each exercise has associated timestamps where you can go in the video and get useful information. Try as many problems from the list as you like and compare your solutions to those provided at the end of the video. This was a Surfing Math lesson. Until the next one.